energy physics, field theory in his early years, and then he moved to, in PhD, to work on more optimization problems, and continued in his postdoc at Paris and Cottington in the same areas. And then he was leading a group at ISI Torino for a while, and since 2011 he's a full professor at University of Paris Marie Curie. And I asked him, and he says his interest can be seen as applying now statistical physics to complex biological systems. And I would say that he's moved really on the side where one only believes when what comes out from the data, and not just from the pure modeling. And it's really a pleasure to have him today with us. And today he will tell us about a particular statistical modeling of protein sequences, and the method he will tell us about has actually become very popular in predicting the structures of proteins.
Thank you for this nice introduction and for inviting me. It was on very short notice because I'm at the moment at the conference in Bangalore, and I said I will just write a greeting to Pierre, and she told me, she wrote me back, why don't you come? And so we just decided on Sunday that I will come for a seminar, and I'm very happy that it worked out. So thank you very much. As was said in the introduction, I'm initially a physicist, mostly a statistical physicist, but in the last 10 years about I have been interested very much in exploring exploring biological problems, and with the spirit of a statistical physicist, or with the methods which are somehow the toolboxes of statistical physicists, because, and I will think I show this quite clearly in my talk, because biology is becoming a science which is very data rich. So there are many methods which produce lots and lots of data, and it's very complicated to come from these data, which are sometimes frequently very large-scale data. So they go to entire genomes and so on, and to go from this data actually to something which is a more deeper understanding of the biology going on, maybe of something which are more fundamental organizing principles of biological systems and so on. And I'm profoundly convinced that actually the approach done in physics sometimes back is something which will be of great benefit also in biology. And so I will talk in particular about protein sequences, and I already mentioned sequencing, and actually in the last years we have seen a very steep increase in the availability of sequence data. Why this? There are very efficient technologies out there for high-throughput sequencing, so you can produce now genomic sequences in very short time. There are tens of thousands of genomes which are sequenced now, as compared, for instance, to the first human genome, which was sequenced only something like 15, 20 years back. And it was an enormous effort. Here in this plot, in this simple plot, you have two curves. One is the spread curve, which is up here, and look at the logarithmic scale, so 100 million sequences. So it's two statistics just made on a database, UniProt database, which is a database which contains all known protein sequences. So whenever a sequence is genome, you can see what the proteins are, which are coded there. They are put into this UniProt database. And you see, it was the increase over the last years was enormous. There was from 2004 to 2014 more or less an increase by a factor of 100. Maybe even a bit faster than exponential, basically due to the fact that in 2007 this high-throughput sequencing I mentioned came around as a technology, and the database actually became so large that in 2015 the curators decided to reorganize it and to reduce redundancies, and so there were some redundancies in there, and they managed to reduce it by a factor of 2. But something as of today. So these are sequences. So you just know the amino acid sequences in terms of. Then there is a sub-database, which is a Swiss prot database, which is this blue line down here, which is kind of flat at 500,000. And this is a database which actually concerns those proteins which have manual annotation. So some human being, some researchers have been working on these proteins, they found out something, and these annotations are put into the database. So these are the proteins where actually we have some actual knowledge about specific proteins. And you see that's flat, 500,000. So it changed from 500,000 here to 550,000 now. So basically no change. This does not mean that biologists became lazy and don't work anymore on proteins. This means basically almost all of these annotations are updated in relatively short time. But it means that biologists tend to work on model organisms like some bacteria like E. coli, Bacillus subtilis, or higher organisms up to human, and work on proteins in these model organisms. So the data here, the actual accumulation of knowledge is not shown by the sheer number, but the annotations are getting better and better for these ones. But still there is kind of an enormous gap which is growing. This is less than 1% of all sequences which have actually an annotation. So are we lost? Should we despair and give up or so? I would like to convince you that actually the opposite is the case. That this enormous increase here is an enormous opportunity because it's providing us many, many data, and from the data, driven by what is hidden in the data, we can actually learn a lot about what these proteins are, and can make a lot of predictions of what is happening with these proteins.
Are these data independently checked? Is the rate at which is growing the data? There not be enough time to recheck these things. Or just taking granted that these data are okay?
Sequencing is a technology which has some error rate, but which is not very high. So at this level, what I'm looking here at, these data are considered to be basically best quality biological data. Other data which are, for instance, talking about for instance, gene expression or so, they are much more noisy. So I will take in this talk data as granted, but since I will use statistical methods, if there are some errors, my results will be a bit noisy. So it's not a real problem. But the redundancy I was talking about was coming in particular also from the fact that some species of interest were sequenced and sequenced again and again. For instance, now we have some thousands of human genomes, tens of thousands of human genomes, which are available, and there's also some natural variability. We are not all genetically equal. And this is kind of subsumed there, and sometimes it's just a consensus which is in there. Okay, so in principle, if we would like to resolve this problem, we would like to go what is called from the genotype to phenotype. So from the sequence, which are these entries of this large database, to more specific knowledge, which is called the phenotype. So the phenotype is actually the physical and biological properties of these proteins, with maybe the structure of the protein. I gave a little example here, which corresponds actually to this amino acid sequence. Part of this corresponds to the amino acid sequence. Protein function, for instance, this protein here, which is this protein here, is involved in some signaling pathway in bacteria. So this is this blob here would be again this protein, and it's interacting, it's doing some biological function which receives some extracellular signals and then changes activates some internal protein which is then binding to DNA and so on. So there's some program, some signaling program which can be activated, and this protein here is part of this. And another point is what actually mutations are doing to this protein. This is something which is very, very important because, for instance, you know that some mutations may cause disease, or other mutations in bacteria may cause drug resistance, and so understanding mutational effects is something which is fundamental importance. So in principle, we would do this. This is very complicated. I can't do this. Some people, some clever people have built models, physical models, for which take all the specific biophysical properties of these different amino acids and make simulations. And for a protein up to about 100 amino acids, for instance, you can predict the structure. Interactions, basically no way. Mutational effects, very little. What I want to do, I'm a statistical physicist, so somewhere statistics must appear. What I want to do, I want to go from genotype variability to phenotype. What do I mean with this? I don't talk about one sequence, so the one we had before is now here evidence in blue, but I talk about many sequences, about what is called a sequence alignment. And why should this give some information? When I'm talking about so-called families of homologous proteins, don't care about this word. What it is these are proteins which have a common evolutionary ancestry. It means they are basically the same proteins either in two different species, but evolving independently since the common ancestor, or sometimes by duplications inside the genome, they are so-called paralogs. What these proteins typically have, they have a highly conserved structure and function. I've just put two proteins here as an example, one over the other, and they are at about 40% sequence identity between them, and you see the structure is basically the same. It's just minor changes. Typically sequences are even more diverged, and that's important. So sequences are very variable. They have something like 20–30% of sequence identity. So this means 70 to 80% of the amino acids have been substituted in the course of evolution. So they look very dissimilar. They look more similar than by random because you may know that there are 20 amino acids. So by random you would expect 1/20, 5% of the amino acids to be common. They have 20–30, so that's much more. But still there is a lot of variability. And I can guarantee you, if you take one of these two proteins, you take randomly 5–10% of the positions and you substitute them, this will not fall into the same. So this means that this strong variability is very constrained by the fact that the protein has to keep this shape, this fold, to maintain this function. It has to do this, and that's why the sequence variability is very much constrained. And these constraints, what I want to do is to go take this alignment of these evolutionary related proteins and infer the constraints to analyze statistically, model statistically the variability which is in the data to actually infer these constraints and to learn something about structure and function. That's kind of the program. So the questions are, can we extract some family-specific signals from these alignments? So like, for instance, the specific structure of this protein, or also in a more principled, more physics type question, can we understand some underlying principles which relate protein evolution on one hand and the functional constraints, structural constraints acting on proteins on the other hand? How they constrain, one constrains the other.
So you said two random sequences will have a match of 5%?
Yeah.
And
it's just because you have 20 amino acids, so if you have take one, the other has the chance 1/20 to be the same.
So can one say if I see a matching of 20 to 30%, is there a number beyond which I can almost be sure that they will fall into the same structure, or this is not?
So this is more about, okay, it's a complicated question. So typically this number is considered to be 40%. But if you talk about natural sequence, if you find a new natural sequence, so a sequence which you know is a protein sequence in some species, and you have it at something like 40% at least sequence identity, you are sure that the structure is very similar. And this is at the basis of maybe the most important structure prediction tool, which is so-called homology modeling. So this homology is detected, and then you just model, you put the structure of the other protein in new sequence together, and you adapt them to each other. This is for a biologically existing sequence. If you take a sequence which has just 40% sequence identity, but you took it, you wrote it down by hand or some random number generator guaranteeing it will probably not fall. So the conditioning to being biologically existing functional is very important in this case. Okay. Obviously, I'm not the first person asking this question. And there, in computational biology, there's some very well-developed methodology, which is called so-called sequence profiles, in which, in the alignment which I showed you before, looks to one column at a time. And for instance, it's hard to see, but if you look down here, there's one column where there's only the letter H. And actually, this is the same is depicted here. You have this H here. And so what the sequence profile do, they go for one column at a time. So each line of this alignment is a protein, each column is a specific position. They look to them, and they look how frequent you have the different amino acids, alanine, cysteine, and so on, in this position. Just count the frequencies. And here, for instance, this would be a lot of histidine. And actually, this protein is called a histidine kinase. So it's not by chance that the histidine is there. So that's the active side of the protein. And you build some statistical model which just says for any sequence which I take, I just look how frequently the amino acid was in this position, and I multiply this frequency. So it's an independent cycle. For each position, I have an independent cycle. So it would be very bad to have something which is not the histidine here, or but in some other position it would be, it's basically unconstrained. These models are very, very important. They are the most important models in bioinformatics. These are the models which are actually used to construct these alignments. These are the models which are used to detect if a protein might be homologous of another one, and I told you then we can use it for structure and functional prediction, and so on. So these are extremely important. They give us a lot of information. For instance, this large H here, so the height of the column corresponds to the entropy. So if it's very high, it means it's very low entropy. So this means I know basically, if I tell you position number 11, I think, you know histidine. If I tell you position number 1, you say, no idea. So it's kind of, the height is the information content which is in the column. So it tells you, for instance, that this position is probably functionally important. This position here is probably important, and actually it's structurally important. It's introducing some kink and some helix. Here, but so you get a lot of information about this. But if you look to this, if you look to these independent positions, they are not really able to give us, for instance, structural information. What does structural information mean? For instance, that in the fold, two positions which are distant along the sequence come together in 3 dimensions. But this is some relation between two. And a model like this cannot do this. It cannot tell us anything about protein-protein interaction, because it's relation between objects, not independent. And don't care about the last point, which is a bit too fast. Okay. What I'm going to tell you is a statistical modeling which goes beyond these independent side profile models, which I showed just before, and which use ideas from statistical physics, and they are based basically on 2 observations. The first one is actually that this idea that positions are independent is wrong. Why is it wrong? Imagine this is a folded protein, so it's a cartoon of a folded protein, and there are 2 positions which are not neighboring, so this is a sequence, a flat one. They are not neighboring in the sequence, but they are coming together in the protein fold. And now if you introduce a mutation in one of these, then it will typically not have the good physical-chemical properties to be in contact with the other one. So typically the stability of the structure will be decreased. So it's deleterious. But maybe you can just repair this by a second mutation in the second position. And if you have this, for instance, here in this handmade case, I have R together with E together with K, but I don't have R together with K, which actually have the same charge. So there's electrostatic repulsion between them, and actually they don't like to be. Whereas these are oppositely charged, and so they like to come together. So, but from a statistical point of view, this is just correlation between them. Correlation means that if I know there's an R, I have a higher chance that there's a D. Okay, now the question is, if I take my alignment, because I told you this is something which I have readily because of this enormous amount of data which are there. If I take some statistical analysis of this, can I actually predict who are the contacts by analysis of correlation? Also, this is not a new idea. It's more than 20 years around. Actually, there's an error. This paper is 92, so it's 25 years. And there has been a lot of work, but it did not work very well, as I will show you in a moment. And I will show you also what the second observation is. So just a bit more technically, what we do to look for correlations. I told you about the profiles. So this Fi was just how many of the different amino acids are there. So this would be 50% R, 50% E in this case. But I don't look only to these two, but I also look to the joint occurrence of two amino acids in the two positions. So this one would be, in this case, 50% RD, 50% EK, 0% RK, 0% ED. Correlation just means mathematically that Fij is different from Fi times Fj. Can be measured by mutual information. Here you have a logarithm of this ratio. So if it's factorizing, this gets 1, the logarithm is 0. And whenever it is not factorized, the mutual information is positive. So it's a correlation measure. So what can I do? I can take my alignment. For each pair, ij of columns, I calculate this thing, this mutual information. That's very fast. It's a few seconds for 30. And then I sort and then just look if the most correlated are in contact or not. I told you that for many protein structures are known, so I can take a protein where I have the alignment, where I have the structure, and I can compare it using only the sequences for the statistic, and then comparing with the structures with some independent information. This is what comes out for one specific case, so-called trypsin inhibitor. I draw here by this, so this blue one is the structure. I draw with these bonds here, these lines, the 30 strongest correlations, which are not too close in distance because these are kind of trivial, but it's also long distance correlation, which are the most interesting. I draw then about against any intuition in red if they are good, and in green if they are wrong predictions. And you see it's a mess. Many green lines which are long, which go from one part to the other part, so which are not contact between these two positions, but still they are correlated. So it doesn't look very well. Still, if you would look to it, it's more than you would have by chance. So there is something. Can we make this see? This is our second observation, and that's basically where the intuition of a statistical physicist starts to enter the game. We were talking about measuring correlation. I was talking in the first place for you about coupling two proteins which are in contact. If I change one and change its physical properties, then it will be more or less well interacting with its neighbor. So that's really interaction, coupling. The two are not the same. You know that if you have a model which has a kind of network or crystal of couplings or so, you can have long-range correlations. So correlations are not necessarily the sign of direct coupling, but they can be mediated by something which looks, for instance, like this. If I and j are coupled to some intermediate positions, and these intermediate positions, so they are coupled indirectly via this, then even if they have no direct interaction between them, they can be highly correlated. Another reason may be that they actually have a coupling between them, that they are correlated. This case is probably not a contact. This case might be a contact. So can we somehow disentangle the two cases? Can we reconstruct somehow the network of these direct couplings, so the red lines from the green lines? And this has to be done by some global statistical models. So this is a probability of a full-length sequence here. Why global? It means I need to know how I and J behave in the context of the others. I don't know who the intermediates are a priori. So I need to know how they behave in the context of all others, if their correlation is explainable by the others or not. So I would like to try to find this model. And how do I do this? This can be done by maximum entropy modeling, so something which is very well known in statistical physics. And there are two conditions which I pose on this model. One is it should have some coherence with the data, because I want to model my data. And the coherence with the data is basically if I take the model and calculate the marginal distribution for two positions, it should coincide with this empirical one. This Fij was what I counted in the data. So I want to reproduce my data at the level of the two-point correlation. This automatically guarantees also the profile of the so the single position, because I can just sum over one more position. Beyond this, I want to have a model which is as little constrained as possible, as flat as possible. And this I imply by maximizing the entropy of the model. So the P minus P log P, sum over all possible configurations of amino acids. And I want to maximize this, so I have a maximization problem under constraint, and I can easily write down the analytical solution of this, the analytical form of this, which is just given by this Boltzmann type distribution here. It's an exponential of the sum over pairwise terms, which are these direct couplings I'm after, so basically the red lines, plus some local biases, local fields, which take care of the fact that, for instance, in position 11 of this example, there's a lot of history.
So what is this HI?
This HI is formally like a local field, but it's just taking care to the fact that in some positions I have some amino acids which are much more frequent than the others.
So it's a distribution, it's picked from the distribution?
It has to, both parameters have to be learned to actually fix this. So it's a fitting procedure. I will come to that in a moment. So if you wouldn't have this colored box here, so that's this one, then you would have an exponential sum over IHI. So this would be a product over I of exponential I. So we would go back to this profile model, which was a product over single site frequencies. So the profile model would be this one without this term. But we have it here. And actually, having it here is from the point of view of. So what we need to do now is we need to fit somehow this E and H such that this is actually fulfilled. So we need to give numbers to this. And this is complicated. This is complicated. Why? Because if you...
I have a question. How do you justify the second assumption of maximizing the entropy? It applies to inorganic systems, but in live systems, I think there is some amount of entropy reduction because you go to an order from disorder.
Yeah, I am not modeling a physical process. I'm just modeling the variability of sequences which are in a database. One must be very careful about the interpretation of these models in terms of anything physical. There's physical signal coming out actually, but this is just here in this point, I'm looking to it more from the point of view of information theory. I just want, this is reasonable because I want to somehow represent my data via a model, and this just means that I take this distribution which is as flat as possible, which does this. So I don't want to introduce anything beyond it. So it's just careful with interpretation.
Question. So this E is your joint probability, right? So you have sequence A. So the exponent, you have just single, AI terms and then AI AJ, but you could have other combination, right? 3, 4, all those terms, right?
Yeah. Okay. There is two answers to this question. When we started to work on this, actually to estimate this, so this Fij here, this is 20 position, 20 possibilities, these are already 400 terms. If you take 3, this is already 8,000 terms, and the alignments were not large enough to even estimate these numbers. So we decided not to look into it. Now sequence alignments are large enough, and there's something mysterious which I don't understand, but which looks very fantastic. If I take this model and fit it very well, and for instance make some Monte Carlo simulation to calculate 3-point correlations from this model, I find actually they fit what is empirically in the data. So it seems that this model reproduce much more of the statistics of the data than actually is introduced here. We have spent quite some time in trying to find these 3-point correlations which we should put in the model. You are completely right. And we don't find any systematic sign for them. This is something which I would like to understand, but this is complicated.
But this also happens in traditional spin models. We know that the
Yes.
3-point interaction is irrelevant in comparison to the 2-point interaction.
Yes.
Is it connected?
It's possibly connected. So you can build up 3-point interaction models which have no 2-point correlations, no magnetizations, but so for instance like a p-spin model on a beta lattice or so.
No, but if you have both.
But if you have both, and probably there is something that actually with these models you can fit a wide class of distributions which relatively well, which even would contain not too strong and not too dominant 3-point terms. So it may be a model, something which is not telling us something about the proteins, but just of the capacity of these models. Okay. So why is it complicated to infer these models? Basically, what I need to calculate is the 2-spin marginal distribution of this global model. So in principle, mathematically, this is just a sum over all the other positions. So this is a sum over 21, so 20 amino acids. You saw that there were these little minuses in the alignment, which are alignment gaps. So 21 possibilities for each of these positions. To the power of the length of the protein would be the total number of configurations. So for a typical protein which has something of the order of 100 amino acids, 21 to the 100 is something which is, could be maybe 21 to the 8 or so, but not 100. No way to do this. There are quite some approximations, so the good news is that you can try a lot of approximations. You can use your statistical physics knowledge about mean field approximations. Also to this, you can go more to things statisticians would do, like pseudo-likelihood maximization and so on. There are different methods. They have advantages and disadvantages. Some are faster, some are more precise, and so on. But so some from our group, some from other groups. The best ones are now meta-classification groups which actually take many of these methods together, do machine learning later and try to be better. But what all these methods do is they strongly improve conduct detection. All of them. Some more, some less, but it's more quantitative difference between the method and the qualitative difference. Here I show you again this example of the trypsin inhibitor. I show the 30 strongest couplings, so the biggest EIJ matrices. And again, all the red are contacts, all the green are non-contacts, and you don't see any gray. In this case, the first green would be the number 32. So there is a reason why I stopped at 30. I show you one specific example, but it works for across many families. So there are 16,000 known families, out of which maybe 1/3, 1/2, between 1/3 and 1/2 have known structures, and it has tested on all of them. If you have sufficient sequences, so at least this alignment has at least about 1,000 sequences, then this works better. Basically always. So, and maybe some families where you have an exception, but almost always the first. So actually this captures something interesting. What is interesting, if you look through this, if you imagine you build this from out of, I don't know, some material, you see this basically looks as if the structure would be well defined. So it looks a bit like the Eiffel Tower, the protein version of the Eiffel Tower. And actually, so the idea might be that you can use the statistical analysis for protein structure prediction. Because I told you that out of these 16,000 families of proteins which exist, something like half don't have known structure. So can we use it? And I show you here two examples which are actually, again, a protein where the structure is known. The known structure are these gray dots which you hardly see, which are underlying. So this is a protein plotted against itself. And whenever there's a gray dot, this means, for instance, here that residue number 20 is in contact with residue number 140. So there's a contact from the beginning to the end. The gray is what we want to predict. What correlation, so mutual information, does is given here by the colored point. Red points are good predictions, so there is a gray point below each red point. Green points are bad predictions, so there is no gray points below the red point. And you see that not only this one has much more red points than this one, but also they are better distributed. For instance, you have some good predictions in here. And these are contacts between the beginning and the end of the protein. If you want to predict the structure, this is something which helps you really. Whereas the correlation are mainly close to the diagonal. So contacts which are very close and they don't give you much information about the structure. And
sorry, so this X and Y axis are the two sequences?
It's one sequence. The sequence against itself.
It's
just that here between 40 and position 40 and position 80 there is no contact.
There is no contact.
But for instance, between position 20 and 100, I don't know, 45, there is a contact.
So that means they are coming closer when the protein forms.
This means that they are in contact and the protein forms. So there is some cut off a certain 8 angstrom distance between the residues in the folded protein. So the gray dots come from a structure, so they are actually the native contact map. They are just like an adjacency matrix of a graph, but this graph is just the contacts.
So
And the colored points are my predictions with the two methods.
So the left-hand side plot has no information about the structure.
Yeah, there's very little information about structure.
We started late.
So the idea may be that one could use this actually to guide protein structure prediction. This has been done now. I have stopped at a certain point adding articles. There was a science article this January by the group of David Baker, who's one of the world champions in protein structure prediction, and they have basically predicted protein structures now for all proteins, which were still missing structures. Not all, but thousands of protein families, which corresponds to millions of proteins. In principle, this predicted structure. So you can use it to guide complex assembly. I will show this in a moment. You can also use it to guide RNA tertiary structure prediction. This kind of information is actually used in a standard way for RNA secondary structure prediction because base pairing in RNA secondary structure, so what's the big base pairing is giving a very strong correlation signal because we have AU and GC as combinations, but many others not. So can be used. I told you that it's used for protein-protein interaction. So we can use it to predict contacts between proteins. Exactly the same method. But what we need in this case is a bit more complicated. So if we have one protein is coming from one protein family, so it has its own alignment, and the second protein, the interaction partner, has its own alignment, this information on itself is not yet sufficient. So what we need to know is who, so in a protein, frequently you have many, several representatives of this protein family. So due to duplication of proteins and so on. So you need to know in principle who of these proteins of the family 1 is interacting with whom of the second. That you can create an alignment where in each line you don't have only one protein, but you have a pair of proteins concatenated to each other, which are interacting. This actually is doing this from scratch is a complicated problem. We have published some paper together or in parallel with another group a few months ago in November. And okay, in limits you can do, and in some cases you can use complementary biological information. Frequently interaction partners are, for instance, co-localized on the genome. They are just one gene close to the other. Okay, if you do this, you can just make the concatenated alignment and just run the algorithm which I showed you before. You can just do the same thing, and then you ask what is the interactions between positions 1 in the first one, the second protein, and these might be proteins. It works. This is a case which actually we started to develop these methods in 2008 for protein-protein interactions. So this is his sensor kinase, which I showed you in the very first slide. This is a protein which I overlaid in the second slide. So these are some more examples from a paper from the Baker group in 2008. And you see that what is in here, these are actually, these look like contacts. If you imagine these red things to be some rubber bands, then it's just pulling one protein into the other. And this is actually used for protein structure prediction. Basically, you do some molecular simulations of these objects and introduce some attractive potentials between along these red lines, and they come together, and this is actually a very good protein structure prediction method. And now there are not thousands like in the single proteins, but tens of structures which have been, so a bit more or less, a bit less than 100 structures, protein complex assemblies which have been predicted. So it's quite interesting. Getting actually experimentally these co-crystal structures of two proteins together is something which is very, very complicated and typically does not work. So there, if you look to structure databases, there's very little protein complexes as compared to single protein structures. Okay. If this works so well, could I ask somehow a more complicated, more general question, which is basically, if I take two protein families, you give me two protein families, and you ask yourself, are these two interacting or not? What I told you here, we knew that this family is interacting with this one, because these are in a signaling pathways, and I know it, and I predicted contacts. Can you give me two arbitrary families, and can I tell you if they are interacting or not? Because I find some coevolution between them or not. Can I actually use this as a discriminator? And this works in a bit less well than the contact prediction because it's more complicated and it's more subtle thickness, but it kind of works. We have done some work here on relatively small interacting systems. Two of them are represented here, which are the large and the small and the large ribosomal subunit. One made out of 20, the other out of 29 proteins. So for those who know, there's a lot of RNA in the ribosomes, which you did not consider because here I was talking only about proteins. And the upper part of this, the upper triangular part here is always the contact map. So this is like the gray dots before. The red parts are the single proteins. So you see a lot of contacts inside the protein. And then once in a while you see some blue dots here, which means that the second protein is actually in contact with this one. It's actually they are interacting. The lower part is a co-spraining of this in terms of a protein-protein interaction, not this this one here would correspond and this one. And the blue level is basically how many contacts are there, so it's kind of a level of how strongly they are integrated. The structures for these ribosomes are known, so that's why this information is known information. I use it as a test case because I have my Curie sequence-based method, and I use this as a test case if my sequence-based method actually reproduces this case. And once I have convinced myself that it works, I can apply it for systems where I don't know the answer. That's what actually at the moment some computers in Italy and France are doing, and so I can't show you the results so far. That's the same system represented in a different way. So now something I forgot to say. So you see these things are very sparse. So most intersections here are white, so that means there is no interaction between them. So here between the 20 protein you have 21 interactions, so 21 pairs are interacting out of existing 190 pairs. Here in the 29, these are 29 interactions out of 406 pairs. So that's a relatively small percentage. So the total percentage is 8-point-something% of all pairs which are interacting. So it's really sparse. And I want to find this sparse signal, which is not, finding sparse signal is always relatively hard. So what we did is we took all these 190 pairs, all these 406 pairs, took the two alignments, ran our method, and looked if actually they have strong signals of coupling between the two families. Then we ranked according to the inter-protein signal, and look what comes out. And this is shown here. So this one is a different representation of the same contact map. Now the gray lines mean where that these two proteins are S3 and R is 14, for instance. Here they are interacting, and the thickness of this line is actually what was the blue level before, so it's proportional to the size of the interface. So thick lines means strong interaction. These very, very thin lines means that they just have a few amino acids which are in contact, and probably they are not. So what we did, we took here in this plot, I showed the 10 first prediction for each of these subunits. And remember that about 8% of all pairs were interacting. So if I would have taken completely randomly 10 predictions in each part, so I would have something like 8% of these 20 predictions would be in contact. Here I have 16 out of these 20, which are actually interactions. You see a few red lines which are not up here, so this means these are wrong predictions. You see these green lines which mostly reproduce the thick gray lines. So what we see are the big interfaces. What we completely miss are small interfaces. That's a limitation of the method for the moment. We can't see small interfaces. We really can't. I have tested this on thousands of protein families so far, and we can't. Maybe in some years we will, but no. But big interfaces we see. And that's already something which is quite interesting, because methods which exist so far are much less precise than this. But you see, it's 80% instead of 8%, so this is very good. We would need larger alignments, because these pairwise alignments sometimes have only 1,000 sequences. And at a certain point, some minutes ago, I told you that we need 1,000 sequences or so at least to have good inference. And actually, all these red lines corresponds to small alignments, which have between 1,000 and 1,500 sequences. So if we would have more sequences, but I showed you the plot about the number of sequences in the beginning, I can just sit down, wait a year or two, and then maybe it will be better.
But are the small interfaces relevant for the structure?
That's a good question. Probably not. Because if you look to the ribosome, actually it's a big blob of RNA with the proteins put on top. So probably the interactions between the proteins and the RNA, which I don't capture here, which in principle one should be able to capture, but nobody tried so far, should be more important. So some of these small things are probably just that they are just one put here, and they contact. So probably many of them are, but the statement I made about we cannot see small interfaces is not based only on ribosomes, but is based on 750 homo dimer families, where actually the interface is functionally important in these cases, or is believed to be functionally important, and we don't see the small ones. Okay. The last point which I mentioned, so this was about protein-protein interactions, and the last point I mentioned was quantifying mutational effects. And I just want to be a bit more precise for why I'm interested in this. I already mentioned that, for instance, mutations may be involved in genetic disease. They may be, they are involved for sure in the evolution of drug resistance, which is a major problem due to multi-drug resistant strains of bacterial pathogens emerging. It is involved in cancer. Onset and proliferation of cancer depend on mutations frequently. And so if we understand something about mutations, we may have some insight for diagnostic and therapeutics. And actually, predictors of mutations are used in almost all biomedical studies. So can we use kind of this framework, this analysis which I told you about, to learn something about mutational effects? And I will tell you in a moment why I think this is interesting. So the most common approach actually to identify important mutation is so-called case control studies. So you have a number of patients, a number of healthy people. You look to their mutation patterns, and maybe there is some significant correlation between some mutations appearing only in the cases but not in the controls. It's typically very limited because, so this is done in so-called genome-wide association studies. Typically very limited by statistics because, in particular, if you have rare diseases, you have just very few patients. In many of these cases, fortunately. But if you want to have this or understand why these people are ill, you can't do this kind of approaches. Our approach is based on evolutionary sequence data, because it's the same approach I showed before. And it may introduce some complementary knowledge in an Bayesian way, but I won't talk about that part, but more about the basic. Okay. Yeah.
We have 10 minutes.
Yeah. Okay. That's sufficient. There are some.
Yeah, I have a question. Have game theoretic approaches also been used for protein evolution?
Game theoretic. There are, I think, game theoretic approaches for instance, protein evolution in a sense of immunology, where you, for instance, have the immune system chasing a virus and the virus escaping from the immune system. I think in these cases there are game theoretic approaches which I use. So I think less for really sequence evolution, but more for the strategies of, because obviously this kind of game. Not really a game of the virus is a pathogen, but okay. So this the inspiration for actually trying this kind of models came from some very recent experimental approaches, large-scale experimental approaches which are able to measure the effect of mutation in thousands of years. So these are high-throughput methods, which this is one of the earlier ones done by the group of Olivier Canaillon, who is a collaborator in Paris. And so the amazing, basically since 2012, it becomes, there are more and more, and now there are many of these studies. And what basically they do here in the case of one protein, which is so-called TEM1, which is a beta-lactamase. Beta-lactamase, penicillin, amoxicillin are so-called beta-lactams. So they are antibiotics, beta-lactams, and if there's an ACE, it means it's an enzyme which cuts this. So these are proteins. This is a protein which in E. coli is responsible for drug resistance. And it's, for instance, a protein which was not present in most E. coli strains many years back, and by now it's present in more than 50% of the E. coli strains. So it's something which is more and more acquired. It's not on the genome, it's on the plasmid, there are some, but due to the presence of antibiotics, probably it's more and more present. So it's a protein which helps E. coli to be resistant to penicillin, amoxicillin, ampicillin, so many of the known antibiotic drugs. So what they did in Olivier Tenayon's book, so in particular Hervé Jacquier, they did some quantitative high-throughput mutagenesis. So what they did is basically they did something which is called error-prone PCR, which is reproducing these sequences with errors. So they produced a lot of variants with them, 10,000 about random mutants, which on average had 2 amino acid mutations, 1.7. 1,700 out of them had no mutation at all at the level of the amino acid, so they are as good as the wild type, so they are the same. But for instance, about 1,000 had distinct single amino acid changes, and some had more, some went up to 7 amino acid changes, but obviously having very little statistical power. And then for all of them, they measured the antibiotic resistance in terms of what is called a minimum inhibitory concentration. So they just put these bacteria into different concentration of antibiotics, and the minimum inhibitory concentration is the minimal concentration where the bacteria do not grow anymore. So at the concentration below, they still grow. And the results are shown here. These white bars are those which are no mutations. So you see that the neutral is this concentration 500, but you see that sometimes you measure also the ones on the side. So this is a measure basically of the precision of the noise, of the error of the experiment. So the error bars are basically from one class to the next one. And then these ones are actually the single mutations. So you see that it is kind of bimodal. Here many are close to neutral. Some, still relatively many, are completely lethal. So they have no resistance at all, at least for the concentration study. And basically there is no sign of actually beneficial mutation. There are some beneficial mutations which are known from more detailed, not high-throughput studies, some 80 out of the possible 6,000 mutations, but they are not really seen. And this is a different representation which shows just for each position what would be the effect to replace the amino acid with alanine, cysteine, and so on. So these are data. We have about 1,000 distinct amino acid changes. Can we predict this? This is a lot of experiment, really a lot of experiment. Can we do something? So I talked to you about this direct coupling analysis, which is my modeling. So what we did is we took for this 10-1 protein, the protein family, so all sequences which are alignable to it. There are about 2,500 distant sequences which are well alignable. We learned the model I was talking about to you, and then we just said, okay, the mutational effect I would assign is just, I take my model, it assigns a probability to the wild type sequence, so to the original sequence. It assigns a probability to the mutated sequence. If the second probability is bigger, then probably it's a good mutation, a beneficial. If it's smaller, it's a bad mutation. So very simple. So what I calculate is basically the fraction of the mutant sequence to the wild type sequence. The probability is the log probability of this having a positive for beneficial, negative for deleterious mutations. This somehow captures evolutionary constraints across diverged homologs. I told you that typically the similarity between this sequence we are talking about and any of these is about 20%. They are very distant. What I want to predict is a single amino acid change in a specific sequence. So there's no a priori reason that they should have to do with each other. One is very large scale, very global things, and one is looking to a fine tuning of the mutational landscape to a fine, local fine scale. So we tested this, and actually what we found was quite amazing in terms of correlation, and this is R squared. This is typically what is called the variance explained by the experiment. So the linear correlation would be the square root of what I'm showing here. The correlation between what our model predicted, so this is this blue one, and what the data are. So the correlation is about 75%. So R squared is 54%. That's quite substantial. And for instance, if you look to things which are based on structural stability, you explain only 10 to 15%, 10 to 20% of the variable. If you take a profile model, which I was talking about at the beginning, so which takes each position independently, you explain 40%. So there is a huge gain in taking actually these couplings into account. Couplings between mutations. There's something which performs pretty well. This is the most used state-of-the-art predictor of mutational effects. In this data set, we outperform it. In other data sets, we perform more or less like so we perform comparable. But this is based on machine learning, on a lot of examples, and this what I showed to you is completely unsupervised. I didn't use any mutational effect data in the first place. So
this improvement is only for a particular set of proteins?
This here is for one specific protein. It has been tested for a number of proteins where these beta sets are there. The profile model is always worse than this one. These are always much worse. This one is lower or equal, let's say. Sometimes it's insignificantly higher. On human proteins, I will show this in a second. No, I don't have it, but on human proteins, this one and this one work equally well, and this is trained for human proteins. So where it's trained, they actually work almost equally.
So the maximum explained variance in all these cases is not more than 0.55?
It's typically less, for most proteins it's less. But what is measured here is drug resistance. So this is very close to what is actually the selective pressure on this protein. In other cases, they measure protein stability, which is not really under selection, and the correlations are smaller. So a phenotype, as I told you in the beginning, is something which is not very well defined. I guess we are better on phenotypes which are closer to what is actually under selection. More than 50% you hardly find. So, what is interesting, it captures somehow the context dependence of mutations. The same mutation into different proteins is different. The profile model cannot capture this because I take each position independently. So, what we did is that we took the protein, so this is CAM1, symbolized by this J. We have the position one position we are interested in, and around this position we make a ball of a certain distance in this three-dimensional structure, and take into account as a context all those amino acids which are inside this ball. So if the ball is very small, it's just a single one, so it's like the independent model. If the ball is bigger than the protein, then it's what I showed you before. But I can somehow, this would take into account just the next neighbors, so the close contacts. And I can calculate this R squared in function of this. And you see it starts by something like 40%, as basically in the plot I showed you before. If I take the direct neighbors, it already went up quite a bit, but it continues to go up to about 20 angstrom. And in different proteins, I always find something between 15 and 20 angstrom, which would be something like shown here, which would be taking not only one shell of nearest neighbor, but a second and a third shell, basically. Still carry information about what's happening here. And then it slowly goes down, and I guess this slowly going down is obviously if I take more and more residues into account, I have more and more parameters in my model, and at a certain point I start to overfit. But it's a very shallow thing in all proteins. So very last slide, just to show you that in principle you can use it on human proteins. We went again to the UniProt database, and there are 75,000 human amino acid variants which are listed in UniProt. Out of them, roughly 1/3 are associated with human disease, many of them lethal. 2/3, a bit less than 2/3, are neutral variants with appearing in different genes. And we use this DCA. And these are the predictions. So this is a so-called ROC, receiver operating curve, which plots, which always, if I take a good prediction, I go a bit up. If I make a bad prediction, I go a bit to the right. So a completely random prediction would be always on the diagonal, and a perfect prediction would go up right to 0, 1, and then go to 1, 1. Anything in the middle is imperfect prediction. And we find with our method something like 82% area under this curve. So random would be 1/2, perfect would be 1/2, which is relatively good, and an independent model would have 71, 74 according to the score. So in principle, it's applicable to this one. The polyphen I showed you before would have 84% here. About would be slightly better, but it's a supervised method. So we are currently working on supervised method, which actually take this into account, and they outperform. But this is work which is pretty much in progress. I hope I convinced you that there's lots of information, and that the statistical physicists can have a lot of fun of looking into this a priori pretty nasty thing. And I'm sure that there's much more in there that I saw. If I would have given the talk to you 5 years back, I would have had much less to tell you, so we found much more information in the last years. And there is much more, I'm sure. And I just want to acknowledge people who were working on the project over the last 10 years almost. I was working on protein sequence modeling, so it's many people, in particular people from my group, are now there or used to be there, and colleagues in several places, and obviously those which paid. Thank you. This was very schematic, obviously. It was very schematic. So if you observe a large correlation, so a large correlation can result from different situations. One is that actually there is a coupling. This introduces a correlation, as I tried to convince you in the slide before. But you can also imagine. So imagine just in a lattice. One atom and an atom which is just the second nearest neighbor. They don't have any direct interaction between them, but they have some intermediates, and they are correlated. So if I don't know what your background is, but if you know statistical physics, for instance, in close to phase transitions, you typically have long-range correlations, even with short-range couplings, and it's just this distinction that you can have long distant correlations which are a collective effect of many intermediates. But if you just determine correlation, you cannot tell apart the two things.
Let's thank Martin once again.
in this database you have annotated mutations. So you know some which are related to human disease and others are neutral. And actually, people thought this is not a good data set because it's a very biased data set, and so people thought about a smaller data set which is extracted from this data set, which contains I think 12,000 mutations if I remember well, which is where you do things with cross validation. So